Okay, so I can go over it again. Yeah. So why is self-attention required, right? If you look at this sentence, it's the animal didn't cross the street because it was too tired. So what is it referring to? It's referring to the animal. We know that as humans, but models might have a hard time figuring out what is the object that a particular word is referring to. So there can be multiple questions that come into mind when you are attending to certain parts of a sentence, and that is what the self-attention architecture encapsulates. Um, so what happens is there are some weight matrices called WQ, WK, and WV. And last time I gave this analogy of the queries being what are the questions you want to ask, and the keys being what are the answers you have, and values being the takeaway. So let's say you have this input thinking machines. So these will be two vectors. Um, each input in a sequence is a vector. So this is, let's say, x1 and x2. Now you multiply this with the query matrix. This is the weight, this is the brains of the model, which figures out what questions to ask from this input. If you multiply x1 with this weight matrix, you will get three values. So x1 times this, x1 times this, x1 times this. You get three values. This is the query, uh, which is kind of like asking what is important or what is the question that you want to ask at this position. So you get these questions ready for all the inputs in the sequence. Then you have a weight matrix of keys, which kind of uh, figures out what is the answer to questions. So you get these keys for these inputs in the sequence. Then you just multiply them together. You take a dot product between questions and answers. And if the dot product is high, it means that the answer matches the question well, basically. Um, so let's look at what self-attention actually does. We'll come to the value part later. So yeah, so for the first input, we take its queries, its keys, and its values, and we multiply its query vector with all the keys or the answer vectors of all of the inputs in the sequence. So we find out what is the match with the question that this position is asking for all the values in that sequence. So we get some value for Q1 dot K1, we get some value for Q1 dot K2, and so on. Then this division by 8 is like a normalizing thing that is an implementation detail in the paper. So it's not very important, but it is important in the sense of stabilizing the training or something. But then once you get these scores represent what is the match between the questions and answers. And you take the softmax, and then you get the scores, which is like converted to probabilities. What you do with this probabilities is you take the value which is there at that position. A value is something like a takeaway, like I said, right? So what is the takeaway that you should take if the question matches the answer? And that is transformed using another weight matrix called WV. And you get this value here, and so on. You multiply this takeaway from each location with the softmax to get a weighted vector, and you multiply V2 with the softmax at that location, and so on, and you add them all together to get the output. So this Z represents what is the overall takeaway from this position, considering all the other positions in the sequence. Um, so this is basically how self-attention works. It is attending to different parts of the input and figuring out what to take away at this position. Yeah. Yeah. We don't. We don't. Yeah, yeah. It is. Yeah, there's no bias added explicitly. It's just an architectural choice which has this implicit intuition that we think about it. And then one way to interpret the results or whether it is doing something similar is look at the attention values, right? So if you look at this is of a trained transformer. So if you look at the attention values you get at any position, it seems like it's doing the same thing. It's attending to parts of the inputs which seems relevant. Yeah, yeah, yeah. So it just gives the model the capability to do that, right? So let's think about what changed between MLP and CNNs. We gave it a capability to look for patterns which are spatially translational invariant, and that's what it ended up doing. So you give the model a capability through design choices, and then you hope that it works. And in this case, it did work. Yeah, there are like so many. Yeah, yeah. So in the original architecture, it was taking a look at the whole input. So it's a fixed length input. If you look at the encoder, right? Um, yeah, you get an input which is of fixed length. So now you would wonder, like, how would you get fixed length inputs in natural language? The sentences are different lengths and so on. We pad them with the null values or like special tokens, which mean that they don't mean anything. So it learns that, okay, if we have padded these values, I don't need to attend to them because it is not useful. Yeah. It still can only do that for certain length. Uh, yeah, yeah. So it looks at all the inputs and everything. So there have been some updates to this transformer architecture. Like there's something called flash attention, which takes some GPU optimizations into use and it does this faster. So what is the complexity of the attention module in terms of the number of tokens? Can anyone take a guess? Like, look at this. Why n cubed? Yeah, it's just n squared because you're using Q1 and taking it with all the Ks, then Q2 with all the Ks, and so on. So it is doing n squared operation in the terms of sequence length. So V's you are just taking, you multiply the input with the WV matrix, you get a V. And now you're just adding them all up. So once you do this operation, this is the uh, operation which takes all of the n inputs in the sequence and then combines it together. You're not doing anything on V, you're just adding it. Also, if you can consider addition also as an operation, then it does like n squared V additions as well. Yeah, so whatever is in the protruding box, that is for each time step you will do n operations, and there are n time steps. So we just now, if you look at this model, um, there is no sense of position, right? If you put machines there and thinking there, you would still get the same results, right? Where is the ordering coming from? Yeah. No, so the softmax would also shift. If you change it like this, let's say the weight matrices were fixed, you just switch the position of thinking and machines. You will get the same Z values but flipped at position. So what is making it learn that there is an order in the input sequence. Right now, we are not even looking at outputs. It's just the encoding stage. So if we jumble all the words in a sentence and pass it the same weight matrices, it will still get the same output, but jumbled in the same permutation, right? Yeah. So that's where positional embedding comes in. Right now, it is not dependent. So if you do that, you will get same values everywhere, but jumbled in the same permutation. So before that, we should talk about how this is done in a matrix form. So for sequences, like let's say a sentence in any language, you will have a sequence of vectors. So that's a 2D matrix kind of, and you multiply it with the weight matrix. You get queries for each position. You get keys for each position, and you get values. Then uh, you do this dot product. It's Q times K of transpose, K transpose, you will get scores. Then you divide this by this this thing which is weird, and then take the softmax and add to all the values, and you get all the outputs. So that's a very fast way to do it. You can parallelize it across GPUs, and it is taking care of the whole input in one go, right? Uh, if you look at LSTMs or RNNs, you will need to do the second step only after you have done the first step, because it needs that H or like the hidden vector from the previous step. Here you don't need that. We are uh, we are taking the softmax. Yeah, the way take the softmax. You said we are adding. Yeah, so uh, yeah. So you multiply the softmax values for each position with the V's, and then you add them together, you get the first one. Yeah. Yeah, it's not totally apparent in this formula. Like it seems like you are just taking the uh, softmax of the V and getting the Z. That is not what's happening. The actual thing happens is this: you take the softmax, you multiply it with V1, and then you take the softmax, you multiply with V2, and then you add all the V's together, which is weighted by the softmax. So, so this is just one self-attention layer, right? Uh, there could be multiple questions you want to ask at the same position. So you just have multiple attention heads, and these have different weight matrices. They will ask different sets of questions. They will have different sets of answers. They'll have different takeaways, and you will get multiple outputs from multiple attention heads. You just concatenate them all together. Um, then you get this long output sequence. Not sequence, it's the output for multiple attention heads, but you still, yeah. For each head, it processes the whole input. It goes through the first head, it also goes through the second head, it also goes through the third head. Each head goes through the whole sentence. Yes. Yeah, so but all these heads are independent. So you can parallelize them. So it doesn't need to wait on anything. You can do it all together. No, so whenever you have an input sequence, you want to pass through the transformer, you you give it the sequence, and then the parallelization is done by libraries like backend libraries, maybe CUDA libraries, which are going to send a particular metrics computation to some kernel or like some core, and then it's getting done. So that is done by backend. We don't need to worry about it. We just write the architecture, and if it is parallelizable, um, the backend code takes care of it. Yeah, so the non-parallelizable operation here is this. Like you cannot get the outputs if you don't have all the inputs here, right? So you need to have all the inputs in one go. So yeah, you have multiple attention heads, you get all these outputs, and then you have a WO matrix, which just transform all these outputs into one set of output. So it is just aggregating all the information you got from all the questioning, answering, and bringing it down to just one set of outputs. So yeah, so now we'll talk about positional encoding. Like right now, there was no positional order. You could replace everything, the permutation of the stuff, and then you will get the same output, but at different positions. But we know that, let's say in natural language, there is meaning in order. So we wanted to know that, okay, this came before this. If we change the order, the whole output should change because that probably means something very different. So, so what you can do with positional embedding is you can use very simple positional embedding, like you just add literal positions to the input vectors. Like you have this embedding x1, this is the input, and you add 0 to it. Then with x2 you add 1 to it, and so on. But this may change the meaning of the input, and it is not very standardized. So what this paper did was they have this weird um, positional embedder. Let me see. Where is this? Yeah. So at a particular position, for all the even places, you have this value, and for all the odd places, you have this value, and and this just turns out to be something like a weird pattern, but it is different for all positions, and you add them to the initial input. So what this embeds into the input is a sense of position, which the model can figure out. Okay, it is at this position, so I need to ask this type of question or whatever. No. So if you look at the uh, this image, right, it is only done here when you pass the inputs. It is after the embedding layer. So you will have inputs. Let's say it's just words. If you have 50,000 words, you'll have a 50,000 dimensional one hot encoded vector representing each word. But we don't typically do that. We have an embedding layer which learns a compact representation of those 50,000. So once you get that embedding, you add this positional embedding and then pass through the encoder. And you do the same thing for the outputs. Uh, yeah. So now look at we are done with the encoder part. We pass the positional encoding. We pass it through multi-head attention, and then there is this addition and normalization, like a residual connection, which passes information from the previous layer to the next layer, and so on. So this is if you know about residual networks, this works very similarly. Then there is feed forward. After you get the output, you also add another feed forward layer, um, which is just adding more bunch of weights to the network. So this is the encoder part. If you look at the decoder, there's an additional step here. First of all, there is masked multi-head attention. So what does this mask mean? And then there is multi-head attention again, which which also takes an input from the encoder. So this is where we do the decoding, which is similar to the LSTM or RNN kind of decoder. So let's take a look at it. Yeah. So when you start with the decoding side, right, you give it an input from here, and that is the input which is transformed into the query. And then this query is attended to by this k and v values. So so you don't get the query from there. You get the output from the encoder, and then there is this matrix called k encoder decoder and v encoder decoder, and you use these inputs uh, as the inputs which you would have used like here. So, yeah, these inputs. So these will come from the decoder, and the WKs, they are getting you multiply the outputs of the encoder to the WK encoder decoder. You get K's K encoder decoder. You get the values V encoder decoder by using the outputs of the encoder with
It's from encoder.
yeah
The three blue ones there. It's the first one.
uh,
They're used.
the three blue, which three ones?
The three blue.
Yeah, so these will go into the input of this yeah, and once you have the output, you have like a sequence, right? You start building a sequence.
First would be the first query would be like
Yeah, I think something like that, which indicates that you have started decoding. Yeah. So based on the output of the encoder and this encoder decoder attention, you get the first output. And then the decoder is used multiple times in a transformer. So you do the encoding once, you have given it a prompt, um, it just generates the encoder outputs. And then afterwards, when you are generating the next token or the next word in the sequence, then you pass it through this decoder with the embedding, and then you get one output. And then you add this here, and then use it again and again. So here we use something called a masked self-attention. Why we use masked self-attention?
query would be I.
The second query would be I. Yeah.
First one would be
Uh, I'm not sure if it is like and in this one. I will look into it and like tell you what is that exactly. But there is something which indicates a start of the decoding stage. And once you get that done, you pass the second, like the first output as the second part from the input, and then so on.
using those
The same weights. Yeah. The encoded outputs are still the same because that is the input sequence you get.
the update on WK code.
uh, no. So once we have trained the model, that then it's done, right? During training?
So like where do we get the WK?
Where do we get?
We do also update decoder.
We, yeah, we do update the decoder part, and like because it's connected through this WK encoder decoder, WV encoder decoder, the gradients flow through that. So that's how they are learned.
Yeah, the code from the
It's not frozen. So once, let's say, yeah, we train end to end because here you will have like multiple. Once you give it a prompt, you will have an error based on the first decoded output, then you'll have an error based on the second decoded output, and that's how it's trained. um,
WQ and the
WQ encode decode, I am not sure. um, I'll have to take a look at it and let you know. Yeah, because I don't see it in the paper. The queries come from the previous decoder layer, and the memory keys and values come from the output of the encoder. This allows every position in the decoder to attend over all positions in the input sequence. So the queries come from the previous decoder layer. You pass the input to the decoder again. You get some queries. It is done in a masked manner. So I will talk about how this is done is masked. Um, and the memory keys and values come from the output of the encoder. So that is basically fixed. Um, like what are the keys and value? What are the keys? It means what are the answers and takeaways that you get from the previous input. So if you look at this one, right? Uh, so these are the context. These are supposed to be the context vectors. You get the attention, you multiply and make software. You get the takeaways. This is something similar like this. These remain fixed, and you take the attention with the new inputs, and here the attention is taken through a neural network, but here you do using the weight matrices, so the K encoder decoder. The queries will remain this, will come from the new parts of the input, the new part of the output decoded. Uh, the previous one, yeah, yeah. So here, what we did was we give it an initial decoding signal. We take an H in it. We get it. Yeah, it's like an AND, which denotes that okay, the encoding is done, and now you should start decoding. So this is given to the decoder, and this is H in it. This will always remain fixed, so you will get H4, right? After you take H4, uh, this is used. Previously, it was used with just one output from the encoder, right? Which was condensing all the information from the input. But here you keep all the encoded inputs, and you use H4 along with H1 to get the score. Like what is the attention score for the first encoder sequence, like input in the sequence. Then you take H4 and H2 and you calculate its attention. You get all these scores for the three vectors, take softmax. And then with the softmax, you give the weight to these vectors and add them together, just like we did for B's, right? And we add them, we get the final output. So this is the context that it is going to use to decode at this stage. So the blue ones are. Yeah, this is corresponding to the Z's. Uh, so in the encoder decoder stage of the self-attention transformer, we have something similar. We get the outputs from the decoder like one by one. Once you have an output, you pass it that, and you take the previous one here. Um, and it does not work like this because it's an LSTM, but you have some input which you get from. So this is the query vector that you will get from transformation of the decoder, and then you use all the outputs of the encoder, take their dot products like Q1 dot K1. So here Q1 will remain from the decoder, and Ks will come from the encoder. So you have this query as like decoder and encoder attention calculation. And then you also have these from the encoder. So that's how you get the final output, which is the, and then it's forwarded directly. So it functions like somewhat similarly, but there's a different way to do it. Um, so this uses something called a masked self-attention. Uh, why is it masked? Is basically because you give a high or very low, like minus infinity values to the future part of the sequence because they have not been decoded yet, right? So let's say the transformation was yeah, so it was this something French, right? And you get the first output I, but I don't know what's going to come later. So you give it a very low attention value by default so that it only attends to things which it has seen so far, because we don't know what's going to come in the future. So in each time step, it will only look at something, things which it has seen so far. So in the first time step, there will be just one layer of attention, like doing it just for the first step. Then for the second, it will do it for everything before that point. Yeah.
How does it look forward generate?
Because it is all fixed, so you have to pass it some token values. So consider an image, right? Maybe you have something where you only have part of the image, but if you pass it through a CNN, which is fixed in architecture, you still have to pad it with something. So you have to pad it with something, but we know that we are at the first time step of decoding. So we only give attention values to the parts of the input before that time step. So we do it in a like fixed manner.
It's a, it's a fixed line.
Yeah, 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 yeah. So once you through all the layers, through all the layers of the decoder, it goes when will generate something, and then you apply a linear layer and then take a softmax, and that softmax it is on vocabulary size, so it will generate one token, and then you pass the embeddings of that token with positional embedding again as the first input, and then everything else still remains zero or whatever.
So that's, yeah, it's not complicated. It's like, it's nonsense for the rest of it.
Yeah. So not that get embedded, that gets embedded, just I gets embedded.
Just like,
Yeah, yeah. And then once you generate the second one, then you do it for the second position as well, and so on. So this is like a good, it also generates at the end like an end of sentence, like a token, which denotes that, okay, I'm done decoding. And this is just how it's trained. So if you take a look at the training data, how this will be trained, this is the original transformer architecture, which was trained on machine translation data, right? So machine translation, you have supervised pairs. You will have something in French, you will have something in English. You just tokenize everything, you have embedding layers and whatever. And then after you are done with the input sequence, you will have some special token which signifies that it's an end of sentence operator. So it learns that, okay, once it has done the translation, it also needs to generate an end of sentence token. So once you during inference time, once you see the end of sentence token, you know that the model is done. So this is the untrained model output. This is the correct and desired output. It is basically the classification cross entropy loss which you can use because it has the final thing is a softmax, and because everything is connected through forward fashion, it will the gradients will flow back through back propagation. Mm. Yeah, this was the original thing was supervised. So let's say you are training it for next word prediction, right? There is something called a causal language modeling loss, which I will touch upon a little bit uh, at the end of the lecture. So I'll let you know a little bit. So, so now just let's take a look at some of the model architectures that are using self-attention. Just to recap, this is how the self-attention operation works. Q represents what questions to ask, K represents what to answer, and B is what to take away. So, so attention is now not slow to compute. You can parallelize it. And because of these residual connections and everything, you take care of the vanishing or exploding gradients as well, even with a long network. So it solves many of these problems. Um, but there are still weaknesses of the transformer architecture. Does anyone care to venture a guess? Information leakage? How? Yeah, but we train it with a clipped mask to take care of that problem. So the main, yeah, yeah, that's the biggest one. So when you talked about context length in the last class, this is the context length which remains fixed for transformer based networks. So once you start training with something, let's say it's a 4000 sequence, like a llama model, trained with 4096, I think. So you are limited to that context length. So you can only generate sequences which are that high in length. Um, it, this was better in RNNs because you could just continue using the same loop again and again for indefinite periods of time. But then you don't get the same information flow from the input and you tend to forget stuff. There's another problem, which is this n squared operation, which is costly because you're doing everything everywhere. So if, especially if it's a very large context size, not everything is going to be useful or not everything is going to be attend worthy. So how do you figure out which tokens are more important and which I need to attend to so that you reduce this time complexity of n squared? Um, yeah, these are some of the limitations of this architecture. So after this was introduced, there were multiple architectures that came up which used this transformer. One of them is BERT, which is still very popular in industry for getting text embeddings and doing all sorts of stuff like search and whatnot. So they trained this using a special type of task, which is you give it a sequence and then you randomly mask 15% of tokens. Like this is a mask token, and you ask it to generate what is that token. So for a given sentence, if you randomly remove 15% of the words, you ask the model to generate those 15% of the words. In this way, it just learns what is the relationship between everything. And this is an encoder only type of um, architecture because here everything can attend to everything. So this is what happens in the encoder. And the output is just you take the output of the encoder and put a fast feed forward neural network and a softmax on top of it to get the outputs. So you don't need a decoder at all. Yeah. Yeah, I mean it has that flavor, but it is not like that. But uh, this is uh this is more like how you structure the training or how you define the self-supervised learning objective. You are randomly removing 15% of the tokens and asking it to predict. So if you look at other self-supervised stuff, right, where what you were doing is randomly breaking up the image and then asking it to predict if you are given this type of pair, what is the position of the second pair. So you're just creating tasks for it to learn, and these signals are naturally present in the data, or something like this, where you're just rotating images and asking it to predict which rotation it is. So, so here what you're doing is you're just randomly masking out 15% of the tokens and asking it to predict. So in this way, because the model doesn't know which 15% are going to be masked. It must understand what is the relationship between words and their positions and so on to be able to accurately predict what is the token at that point. Yes. Sorry, I didn't get. Yeah, so it does not generate. BERT model does not generate. It will give you an embedding of the input. So once you are done with this mask, right, training and everything, you just pass it a sentence, and you will get corresponding embeddings at the output. And those embeddings are very useful. Yeah. So yeah, it is a self-supervised learned model because you are randomly creating this 15% fulfilling task. So it just learns a good representation of the English language if you train it for so many sentences, and then you just pass new sentences to it and see what the embeddings mean. So people have used it for like sentence classification, sentiment classification. I mean, whatever you can think of in NLP, you can pass the input through BERT, and you will get some embeddings and use those embeddings in a let's say if you have a small semi-supervised like data set, you just train a feed forward layer on top of these embeddings, and you get good performance for new inputs. Yeah, yeah. Yeah. So when you have limited training data, then you worry about generalization. What these models are trained on is basically a huge amount of the internet data. It has seen so much that it is unlikely that it has not seen a very natural sentence. So the problem of generalization still exists. Like if something novel comes and people are writing, if Donald Trump is not the president of the US anymore. So these models are susceptible to those kind of problems because the knowledge in the world updates like every day, right? But once you have trained the data, trained the model on some data which is fixed, the model's knowledge is fixed. So now it can't really update everything. So initial versions of ChatGPT were trained on models before 2020, right? So if you asked it to predict who was the president of US, it would predict Donald Trump. So that's a problem, and that's an active area of research, like how to not retrain the model again with new data, but just augment it with something like fine tune it or whatever in a small amount of time and compute, so that you can update the information. Yeah, yeah. So people like this transformer architecture was so powerful that people just started using it a lot, and then people scaled it up. And like training one GPT-3 instance takes like millions of dollars, but they because the output performance is so good, they did not worry about these problems a lot. But now we know that these problems exist. Now people are trying to figure it out. But we have invested in so much, like multiple companies spending millions of dollars every day. So yeah. So like the objective of this course is to excite people like you to come up with solutions to this problem. Maybe come up with a new architecture. Yeah, I'm trying, but like I don't have a solution yet. So this is BERT, um, which is a type of transformer which we call encoder only, because it's using just the encoder type of structure. GPT is trained in decoder only mode. So here what you do is you leave away the encoder. There's no encoder decoder attention. It's just decoder. You give it the first input and then you pass it through the decoder and you ask it to produce the output, which is the second one. And then you pass it again, the first and second input, and do this again and again. So here's how you would do self-supervised learning. Like once you have um, infinite amount of text data, you just pass it sentences like this. You give it the first word in the sentence, then ask it to predict the second. Can you close the door? So give it part of the sentence and then ask it to predict the next word. That's it. So that's also self-supervised, like a very simple objective. Uh, you don't need to even randomly mask 15% of tokens out, and you use just the decoder part of the network. It uses masked self-attention, and that's how you get uh, GPTs. So all of the GPTs are trained in this manner. You just increase the number of layers, number of heads in each layer, uh, the embedding size, and so on. GPT-2 could process 1024 tokens. So that was the context length of GPT-2. GPT-3, I think, could do 4,000 or maybe 8,000. Now GPT-4, I think, can do 32,000. Google Gemini can do 1.5 million, but it's not doing the same thing as the transformer. Like it's not doing n squared operation on 1.5 million context. They have some new techniques where they figure out what tokens to attend to, what not to, and so on. There's also text to image models like Dolly, where they train somehow like similar to clip data, like the clip model. You have some captions, you have some images. You ask it to generate images according to the captions. I'll not go into the detail of this. It is just to show you what's there. Sorry. Yeah, the clip model is again, we talked about it previously, uses vision transformer. So the transformer is used in vision as well. And how you can use transformers in vision is you take like random patches in the image and attend one patch to the other patch to make like long range connections. So the CNN, if you look at the CNN architecture, it takes a look at just the local structure where the kernel is only focused on that part of the image. But it doesn't take care of the long range stuff. What does this part of the image mean for this part of the image and so on. So vision transformers do that, and they are also very successful. And now we have like anything to anything models where you can give it text, image, video, whatever, and it will produce text, image, video, code, whatever. So that is where we are headed. And what's next is like some of these questions like are these anything to anything models going to work best for everything? So let's say you train a huge model with all sorts of data, like, and it can do anything to anything. Do you think it would be best at doing everything? Sorry? Yeah, exactly. So it would be jack of all trades, but if you wanted to do something very specific like machine translation, maybe it's not best at that. So, but what it can be best at is generating meaningful representations for everything. And then you can use those representations to do fine tuning on whatever task you care for. So that's the hope. So the tail of the distribution is still hard to catch, and we still find best model for downstream tasks are fine tuned. Um, and what are some applications that these model are still not capable of solving? Like we have seen, yeah, math. Yeah, I mean, yeah, that is true. We have seen some benchmarks where they claim that okay, GPT can do elementary math, and then GPT could do 10th standard math, and then GPT can do med school stuff, like USMLE it can cross or whatever. But I think those are fine-tuned models. Like you train it on the whole text and then you fine-tune on USMLE, whatever data set. So they are not able to solve all of the stuff, especially in applications like medicine or robotics or any non-image text problems because of lack of massive data sets. If you wanted to do radiology, it can't really do that because there's not so much of data present compared to text and image on the internet. Um, Also for robotics, you need to build a robot and then collect data and then do it in a self-supervised manner. That kind of data is not really available. So there are problems that these models cannot solve. And the success of these models is mostly um, due to the internet, basically. You have internet, people are posting stuff, you get so much data for free. And we just figured out a tricky way, like not tricky, it's a trick that just make the model learn patterns in data and create artificial tasks like 15% token removal or next word prediction and so on. And what can we as scholars do to make this happen is we can find inefficiencies in the model. Like we found out that it is a fixed token length, so we cannot do infinite sequences. We cannot pass it the whole book and ask it to come up with a new chapter or something. Um, so what we figure out these inefficiencies, we figure out problems like knowledge outdatation, and we try to develop better models and algorithm for it. Yeah, so that's it from the slide part of it. I will show a little demo about um, using BERT and CLIP models. So there's a library called transformers. From there you can install all kinds of models with which have pre-trained weights available. So so this is a BERT tokenizer and BERT model. The BERT tokenizer does the same thing the tokenizer would do in the transformer model. It is learned, it has like pre-learned weight matrices, and you can just load it very simply like this. You have BERT tokenizer from pre-trained, and these are the weights. Now, there's a sentence like, I really enjoyed this. Uh, I really enjoyed this movie a lot, or whatever. So we first tokenize the sentence. We get tokens like this, and then we add these special tokens which the BERT embedder knows, like okay, these are start and end of the sentence and whatever.
CLS thinking.
It's a class. I don't know exactly, but this is like a special token which indicates to the BERT model, okay, I want something to be done with this. So this is like a classification type of embedding. So, so what do you want this? Sorry, sorry.
What do you say?
So it indicates like when you give the separator token, I think this indicates that the sentence has ended, and whatever is uh, beyond this, it's just bad. So like I just have this, which I need to really take care of. This is the start or whatever, and this is the end, and this is just padding. So it will have a fixed input length, right? So you just pass this fixed input length, and you get the output. So then there is this attention mask. So if you remember that it was masked attention, we can also give it a masked attention in BERT because we only wanted to attend to this part of the image. The other is padded. So it will just give zero weights to all the other attentions.
It's supposed to be is like 100% of the.
No, this is the length of the sequence which goes into BERT. But because this is not 15, we pad the other stuff. Yeah. And then we get some like bookkeeping, which is done for these are the IDs that you get out of the tokens. So there would be there is a vocabulary, predefined vocabulary, and this sentence has these IDs in that vocabulary and so on. So this is attention and segment, and then we just pass the input to the model. This is the attention mask. This is the token type IDs, some bookkeeping, and so there you get 15 embeddings because for each of the token you get some embedding. Uh, but you just use the first one, which is like the CLS token because it has a special meaning. So we just take the 768 dimensional embedding and we can use it for anything we want. So now we have another sentence called I did not like this movie, which is different from I really enjoyed this movie. And then sentence three called I hated this movie. So if you were to imagine uh, what is the similarity between sentence one and sentence two and sentence three, what would you think it would be? Sentence two and three are similar, and sentence one is different, right? So we pass the sentence two through the model again, and we get sentence two embedding, and we pass sentence three through the model, we get sentence three's embedding, and we just print their dot product, right? So sentence one times sentence two, one times three, and two times three. So one is different from two and three, right? So we expect these two values to be low and the third one to be high, right? So if we run this, we get 264, 267, and 321. If we use like softmax or whatever, then we can use this as a direction to find similarity between sentences and so on. So you can use pre-trained models for any downstream application you want. Also, yeah.
What's gonna be in low God? We know that, the most. So how do we know it has to love
Yeah, we don't. We don't. So if you want to do some downstream classification type of task, you will have to figure out this threshold. Like what is the threshold after which you cross the similar regime to dissimilar from dissimilar regime? Because these embeddings are very generic, right? So you don't know exactly what is going to be the similarity between a very downstream task which no one has really done. So if you have some data regarding that task, you calculate bunch of dot products, you figure out what's the good threshold, and then you use that threshold for any future task.
So if you we don't.
There would be definitely like people have used BERT for so many different things. So this would definitely have been done. I'm just telling you one way to do it.
Yeah.
Then there is the clip model, which is the image and text model. So you give it an image, you give it multiple text. Remember zero shot classification from here. You give it an image, you give it a bunch of text, and you want to do classification. So here we have the clip model loaded into memory, and we have two URLs. One is of a cat and one is of a dog. You can look at the images as well. So this is the cat and this is the dog, right? We give it this URL. It opens the image for, let's say, cat. And there are two sentences, a photo of a cat, a photo of a dog. We expect the first one to have a high alignment with the image, right? So we pass this input to the model. This model generates multiple outputs. It has logits per image. It has logits per text. It has text embeddings. It has image embeddings. So, sorry. Yeah, clip. So you get logits per image means what is the logit for each text you get for each image. So for each image, there is only one image. We get two for them, and it is 18.9 and 11.7. And for each text, because we only have one image, it's just a transpose. So we have 18.9 and 11.7. If we take the logits per image and we take the softmax, we get a very high value on the cat's text, and very low value on the dog's text. And if we change it to dog, so it's running again, and this time we have the opposite. It has like 99% a dog. Yeah. So it is taking the image, it is taking the text, it is calculating embeddings for the text, it is calculating embeddings for the image, and just start producting them. So you remember this thing, right? It is trained in this manner with a contrastive loss. You take a bunch of images, you take its corresponding caption and some random captions. No, there's no BERT here. It's just clip. I just showed you in the same demo, like how you can use BERT, and then I showed you how you can use clip. Sorry? It has a text encoder, it has a image encoder. I gave it an image of a dog. It got the image embedding, right? Sorry, the next slide. This one. Gave it an image of a dog and got an image embedding. I gave it two uh, text, right? A photo of a dog, a photo of a cat. You get two embeddings of uh, those texts, and then you calculate the dot product, and these were the values that you get. These two values, and then you can use softmax to just do zero shot classification. Now it's up to you. Like you can come up with a very novel task, which can be done with the text and image pairs, and then evaluate clip on it. Like how generic or how good are these embeddings? Yeah, so that's probably it. Yeah, so I wanted to show a little bit of this, but I don't think we'll have enough time. So there is this repository called NanoGPT. It's developed by Andre Karpathy, who is a renowned computer scientist. And he basically, yeah, you can use this to train your own GPT model on whatever data that you have. And it is written from scratch. So you can find everything that is relevant for training your GPT in the same repository. It's very lightweight. Uh, it has this layer norm, which is used there. It has causal self-attention, which is the next word prediction task. uh, and then it has an MLP module and a block of transformers. And the GPT has this transformer uh, model inside it, and you can train it. You can do the forward operation. It just goes through the whole GPT layer. You can take a look at it, and if you think you want to implement it or something, you can. And if you are having trouble, you can just shoot me an email. I don't want to get into this because this is an ML class. It's not even deep learning. And this stuff you will probably learn in a self-supervised learning class from Daniel. So, sorry. Yeah, you can just search Nano GPT or I can provide the link. Yeah, that's it for today. Yeah, it's not my dog. It's from the internet.